All right, welcome back, students. This video we're going to do the second half of 11.8. This is applying similarity to solid figures. Sorry, couldn't remember what it was called. All right, so we're on the back page of 11.8. To go a little quicker. So top here we're learning similar solids. So two solids are similar if and only if they have the same shape. Obviously, got to be, if it's a cone, it's got to be a cone. And the ratios of their corresponding linear measures are equal. So height 1 to height 2 would be equal to radius 1, radius 2. All right, over here, so if two similar solids have a scale factor of A to B, then the surface areas of the ratio will be a squared to b squared, and the volumes will be a cubed to b cubed. So here's our example. So if your scale factor is 2 to 3, so 2 to 3, then your ratio would be 2 squared, or 2 times 2, which is 4, to 3. 3 times 3, or 3 squared, is 9. And then the volume, so that's cubed. 2 times 2 is 4, times 2 is 8. Or 2 cubed is 8. 3 times 3 is 9, and times 3 is 27, or 3 cubed is 27. Kind of what I was saying in the last video, kind of getting ahead of myself, but that's what we did. We weren't dealing with surface areas, but we were dealing with the base area. The linear part is A to B. You square it when you're talking about area, then volume is cubed. All right, so two solids are congruent solids if and only if they have the following characteristics. So corresponding angles are congruent, corresponding edges are congruent, corresponding faces are congruent, the volumes are equal. So it goes further here because we've talked about congruent figures and they'll have bases and sides. Well, three-dimensional, they have angles, edges, faces, volumes, because they can be filled with something. They're not a flat surface there. But in this case, so your height 1 to height 2, your slant height 1 to slant height 2 would all be, these would be equal, or the ratio would be 1. Okay, so we got a example and a check. The check is easy, or much easier, I think, than this, but it's not bad. So for example 4, so we have 3 cones that are similar. Find the volume of each cone. All right, so they don't give us the height. They give us, this is the slant height, and we need height in order to find the volume of the cones. I can tell you, so 1 and 3, they both have the same radius. These are, I'm just going to write here, cone 1 is congruent to cone 3. Same shape, same dimensions. So under here, when we find the volume of cone 1 over here, when we get to cone 3, we're going to duplicate that. Excuse me. So from 1 to 2, our scale factor, new to old, is 6 over 5. So when you're talking about volume, so when we get over here to cone 2, we're going to cube those as we're talking volume. So scale factor will be 6 over 5 cubed. So we're going to take the volume of 1, multiply it by this. So let's go ahead, just to work this, before we find the volume of cone 1. So 6, and remember, let me just pull this up here. So this is square root. If we want to go anything besides square, so if we're trying to cube or to the 4th power or whatever, we use this button. Now we don't have a separate button for cube root, but notice above here it's got an X on the outside. That's because if you were to take the cube root, it'd be a 3 on the outside of the box. So to cube root, you'd use the second button, but if you're just trying to cube something, it's this. So 6 cubed, 6, then you hit this button, and then the X is what you're filling in. So it's cubed, so it's 3. So that's technically telling it 6 to the third power. That's 216, just to prove that I'm right. So 6 times 6, that would be squaring it. That's 36, and then you multiply another 6, that's cubing it, 216. So 216 on the top, and on the bottom, so 5 times 5 is 25, times 5 is 125, but to prove, so 5 cubed, 125, or again, 5 times 5, 25 times 5, 125. So you're going to multiply that volume of cone 1. So, but before we go there, I don't have as many pens and such over here. So to find the true height, you would have our dotted line that goes, well, it's actually here, not there, so it would be perpendicular here, and we end up with the top is the radius, that's your 5. And the slant, so it'd be this, same, it's 12. So this is our 90-degree angle, so that's 12. We're looking for this. That's the true height. So that's what that dotted line is. So we're using Pythagorean theorem, this being our hypotenuse. So it would be 12 squared minus 5 squared would give us our height squared. Just changing this from A or B to H to suit us. And remember, the hypotenuse is always across from the 90-degree angle, and if you have it, you're going to subtract. If you need it, you're going to add. So 12 squared is 144. 5 squared is 25. Hold on. Gives you 119, and so your height is the square root of 119. Let's do this over here. So your volume, base area times height. We're substituting because the base of these cones are circles, so it's pi r squared times the height. We have the radius, so it's pi 5 squared, and then height. So height here, it's square root of 119. We're just going to find that real number. So that's 10.9. So over here, we're taking 5 squared times 10.9 equals times, so it'd be 272 and a half pi, because we still got pi to go, so pi equals, so 856.08. We're just going to leave that at 856. So volume's 856 cubic inches. All right, so now we're going to take, 856 times, now, so 216 divided by 125, so that's 1.728. So, oops. So times, that gives us 1479, and we're going to just round it to 1479. So the volume of cone 2 is going to be 1479 cubic inches. Now we did that because we took the scale factor, multiplied it by this. We didn't have to do the same thing here. Now we could, and then you could just check your formula to see if it's the same as this, but trust me. Now, over here, 856, remember I told you 1 and 3 are congruent, so therefore, guy's 856 cubic inches too. We're way off the page there. Pardon. So, moving down, and this is taking longer. So, example 2. So you're going to go, so prism 1, volume is base area times height. This is a rectangle, so it's length times width times height. So you're just, see, this is how wide, how tall it is, or the height. This is how wide, this is the length. So you're just multiplying these 3 numbers. If you look, the scale factor from new to old here is a half. So this should be half of this, and this should be half of that. But if you take the whole volume and then use the scale factor cubed, you can get the volume of this. These 2 are congruent. I'll just give you that. So prism 1 congruent to prism 3. So for the volume for prism 3, put it under here. You got 1, and then 2. Just take volume of 1 times scale factor cubed. I told you the scale factor, and then that should help you. So, see what you get there. I'm going to flip over. 2 of these left. So, you guys are going to do the check down here. It's going to be 2 similar cylinders. This one up here, 2 rectangular prisms, square bases. So, square base means that all 4 sides are congruent. Has surface area of 98. And let's see, the other one is 18. So new to old is 18 over 98. Now these are surface areas. So surface areas is going to be squared. So if we want the scale factor, we're going to have to take the square root. Now we have 9 for 1. So we're looking for the smaller. So we went new over old. So it would be, if we're looking for the smaller one, that's going to be X. Excuse me. Let me see. But really, because, actually, forget this. We're going to multiply 9 times this. So find the scale factor. Excuse me. So because these are surface areas, that's why they would be the scale factor squared, so we need to take the square root. Now, we can't, these aren't perfect squares, but I know half of 18 is 9, and I know half of 98 is 49, and those are perfect squares because the square root of 9 is 3, and the square root of 49 is 7. So this is the scale factor. But step 1, find scale factor. And that's what we did, because the surface areas, that's the scale factor squared, so we took the square root. We just took half of that so we could pull this number out of that. All right, step 2, we're going to find the length of base of the smaller base edge. And then it wants the perimeter. So 3 is find perimeter. And perimeter, because it's a square, it's going to be 4 times whatever this is, the side. So 4 times what we find over here. Now, to find that side, so we know the larger one's 9. We know the scale factor is 3 over 7. So just multiply those. So 9 times 3 is 27 over 7. 27 divided by 7 means that side is 3.857. We're going to round that up to 3.86. So the side length, and these are centimeters. the perimeter. So 4 times 3.86. All right, be 14.2. They didn't say it around. We're just gonna, yeah, we'll round down. 14.2 centimeters is what the perimeter is, because the perimeter's all 4 sides. Remember, so these were all 3.86, and each one of them's the same. So that's why we multiplied it by 4. That's how we got that. All right, so you guys are going to find the similar cylinders. They have volumes. Here's your volumes. So you're going to go like 640, cut the pi out. So 640 over 270, but this is going to be, you're going to need to take the cube root because these are volumes. And then, so the height, once you know the cube root, just take the height, the one height, 10, and multiply it, and that'll give you the smaller height. So 10 times scale factor, once you find it here, will give you, this is, small, because the larger height is 10. And that'll give you the smaller height, and then use that to find the area of the base of the smaller cylinder. Okay, hopefully it didn't confuse you guys too much. Kind of all over the place. This is being the end of the book. It gets a little tougher, and but hopefully you guys got something out of it. Please let me know if you have any questions. Until next time, have a good night.